I welcome you all for this video. This video is about Gaussian integers. In abstract algebra, Gaussian integers are a fundamental example of a ring extension of the integers, showcasing how algebraic structures can be expanded to include complex numbers while still retaining many familiar arithmetic properties. The study about Gaussian integer useful in solving Diophantine equations, example, Fermat's two-square theorem. It appears in number theory, cryptography, and algebraic geometry, and used to extend results from integers to more general algebraic settings. Now we see what is Gaussian integer. Gaussian integers are complex numbers. Their real and imaginary parts are integers. They are closed under both addition and multiplication. We will check it now. They contain standard integers as a subset. The set of all Gaussian integer is denoted as z of I, which is set of all a plus bi. Here, a and b are integers. For example, 3 plus 2i belongs to z of I, where 3 and 2 are integers, whereas 3 by 2 plus 2.5i doesn't belongs to z of I. It is not a Gaussian integer because 3 by 2 and 2.5 are not integers. Now we see z of I is a ring. To check whether z of I is a ring or not, we have to check the axioms: abelian group under addition, closed and associative under multiplication, and two distributive laws. We check one by one. Now, first we check closure under addition and multiplication. For that, let us take z1 is equal to a plus bi and z2 equal to c plus di from set of all Gaussian integers. Here, a, b, c, d are all integers. Now we check for addition. That is, z1 plus z2 can be written as a plus bi plus c plus di. We can rewrite this as a plus c plus b plus d I. Here, a plus c and b plus d both belongs to z since a, b, c, d are integers. Therefore, z1 plus z2 belongs to z of I. Now, we check closure property under multiplication. That is z1 into z2, which is a plus bi and c plus di. If we multiply these two, we will get ac plus adi, bci minus bd. Now we try to rewrite this as ac minus this is ac minus ac minus bd plus AD plus BC I. Here, AC minus BD and AD plus BC belongs to Z. Since A, B, C, D are integers. Therefore, Z1 into Z2 this is Z1 product Z2. Z1 into Z2 belongs to Z of I. Now we verified that Z of I is closed under addition and multiplication. That is, we checked this one and this one. Now we prove associativity of addition and multiplication. It follows directly from the associativity of integer addition and multiplication. So we skip this now. It directly comes from associativity of integers. So now we check existence of additive identity. The element zero plus zero I, simply we can write as 0 is in Z of I, since 0 is an integer. Therefore, 0 belongs to Z of I. Therefore, additive identity is also exist. Now, we check for additive inverse, that is existence of additive inverse. For Z is equal to A plus BI, the additive inverse is minus Z, which can be write as minus A plus minus BI, which is also belongs to Z of I. Since AB are integer, minus A minus B also integers. Therefore, minus Z also belongs to Z of I. Now, we verified that additive inverse also exists. Next, we prove that Z of I satisfies commutative under addition. For that, we prove commutative property now. For that, we take two elements, Z1, which is as usual A plus BI, Z2, C plus DI belongs to Z of I, where A, B, C, D all are integers. Now, Z1 plus Z2 is A plus BI plus C plus DI. Now, this is A plus C plus B plus DI. Now, go for Z2 plus Z1, which is C plus A plus D plus B I. Both are same. Z1 plus Z2 equal to Z2 plus Z1. Therefore, Z of I satisfies commutative property under addition. This is also over. Now, we have to check two distributive laws. For x, y, z from z of I, we can write x times y plus z is xy plus xz, and x plus y into z is can be written as xz plus yz. Follows from integer multiplication and distributive laws. Therefore, z of phi satisfies distributive laws. These two also over. So is z of phi satisfies all the axioms of rings. Therefore, we can say that z of phi is a ring. Next, we check z of phi is an integral domain. First, we see what is integral domain. If the ring is commutative as a multiplicative identity and has no zero divisor, then the ring is called as integral domain. Already, we proved that ring satisfies the commutative property under addition. Now, here we need to check it is commutative under multiplication and has no zero divisor. These two things we have to check now. First, we check it has no zero divisor. That is AB equal to 0 implies either A equal to 0 or B equal to 0. This is what we need to prove in order to check whether this has no zero divisor or not. Next, we have to check commutative under multiplication. We check one by one. First, we prove the first one. Suppose A plus BI, C plus DI are two Gaussian integers, their multiplication 0. This is what we have to take. And we have to check either of them are 0. By multiplying these two, we get AC minus BD plus AD plus BC I equal to 0. 0 can be written as 0 plus 0I. Now, comparing both sides, we will get AC minus BD equal to 0 and AD plus BC equal to 0. So, from the second equation, we can rewrite AD is equal to minus BC. Since A, B, C, D are integers, the only integer solution satisfying both the equations are when either A equal to 0, B equal to 0 or C equal to D equal to 0. This gives us Z1 is equal to 0 or Z2 equal to 0. Thus, Z of phi has no zero divisor, meaning it is an integral domain. It remains to prove its commutative under multiplication. Now we check commutative property. To prove commutative property, Z1 A plus Bi and Z2 C plus Di to Gaussian integer. Their product Z1 into Z2, it is AC minus BD plus AD plus BCI, which is same as Z2 into Z1 by the commutative property of integer numbers. So Z1 into Z2 is equal to Z2 into Z1. Therefore, it is commutative under multiplication, and we prove that it has no zero divisor. Therefore, Z of I is an integral domain. Next, we check Z of I is a field. First, we see what is field. A field is a commutative ring where every non-zero element has multiplicative inverse. That is, for every Z A plus Bi Gaussian integer, which is non-zero, there must exist Z inverse x plus yi by m in Z of I, where x, y, m belongs to integers. This is what we need to prove to check Z of I is a field. First, we go for the multiplicative inverse of Z. Here it is taken as A plus Bi. And Z inverse, this is a complex number. So Z inverse is 1 by A plus Bi. We multiply and divide by its complex conjugate A minus Bi divided by A minus Bi, which is A minus Bi divided by A square plus B square. This can be written as A plus A by A square plus B square minus Bi by A square plus B square. Here we need to check this number A divided by A square plus B square and this number B divided by A square plus B square are integers. If they are integers, then only we can say that this Z inverse belongs to Z of I. But these two numbers need not to be integers. We can give a counter example. Consider Z is equal to 2 plus I. Its inverse 1 by 2 plus I. Multiply and divide by its complex conjugate 2 minus I divided by 2 minus I, which is 2 minus I divided by 2 square plus 1 square, which is 2 minus I divided by 5. This can be written as 2 by 5 minus I by 5. Here 2 by 5 and 1 by 5 are not integers. Therefore, Gaussian integer may not have multiplicative inverse in Z of I. So, it is need not to be field. It is not a field. It need not to have inverse. So, it is not a field. Thus, not all elements have inverse in Z of I. Therefore, Z of I is not a field. So far, we discussed what is Gaussian integer and checked whether the set of all Gaussian integer is a ring, an integral domain, and a field. We conclude that Z of I is a ring and it is an integral domain and it is not a field. In the next video, we try to prove that Z of I is an Euclidean ring and we will discuss more properties about Gaussian integer. In the description of this video, we have attached the notes, the materials for this lecture, and we attached a quiz related to Gaussian integer. Please, viewers, attempt the quiz and check your insights in Gaussian integers. Thank you. We will see in the next video.